Hey everyone, this will be a video on section 2.4, which is talking about polynomial and rational functions. And I will put a disclaimer that for this particular section, a lot of the problems, there is, how should I say, a very long way to do the problems that you might see on your MyLab if you have them guide you through the problem. But for any of the questions we talk about, you can always graph the question, or the function, I should say, with Desmos, and then use that to help you answer any questions, and that's perfectly fine. Okay. So a polynomial is a function that can be written in this format here. So you'll notice there's a lot of variables, okay, different things. So a to the n is just, so you want to think, we'll just go through the piece by piece. Integer n, that's the highest number here, because then the next one is n minus 1 and so forth. That's the degree. The coefficients, all the a's are coefficients, and they're real numbers. And you have it where the highest one, the leading coefficient, right, the an, goes with the highest degree. So the domain of any polynomial function is all reals. You might see it written like this, or you might see it written in interval notation like this. Now, some examples of a polynomial. So let's say n was 3. Then I could say, let's say I had 4x to the third minus 2x squared plus 5x plus 10. This would be a polynomial. See, I have it written where x's, the powers are 3, and then the next term is 2. So this one has a third power, this one has a second, a first, and there's no x here, okay? And we see that the last one here doesn't have an x. And then the numbers beside the x, those are the coefficients. So this term here has a coefficient of 4. This one has a coefficient of minus 2. This one of 5, and this one is just, constant coefficient term, or constant term, as some people will say. So if your polynomial has a degree 0, that means it only has this. This is a constant function. If it has a degree, so that would mean if I just had 10, if I just said f of x is 10, then that's always going to be 10 for any x, so that's why it's a constant, it's staying the same. If your polynomial has degree 1, that means the highest x is to the first power. Let's say if I had f of x equals minus 3x plus 7. What type of function is this? This is, we did these earlier, this is a linear function. And then degree 2, let's say I had 4x squared minus 10x plus 8. Okay. So what would this be? So this is what we did last, so it'd be a quadratic. Oh, excuse me. So we're going to look at some of the graphs here. I do apologize. So we see here that for the figure A, B, and C, so here is figure A, here is figure B, and here is figure C. That, just to practice, this is degree 1. You see the highest x has the first power. This is degree 3, and this is degree 5. Now you'll notice, like for degree 3, I don't have an x squared, and I don't see a number without an x. Perfectly fine. Okay. You don't have to have all the x's after the highest one. Okay. It can mix and match. You'll notice for degree 1, it crosses, looks like it crosses once. And then it's lower on the left, higher on the right. And then for degree 3, same, lower on the left, higher on the right. Same down here also for degree 5. You'll notice what happens. It goes up, and then it turns, comes back down. It crosses 1, 2, 3 times, and this one crosses 1, 2, 3, 4, 5 times. And it curves once, twice, 3, 4 times. So this is just one example. I kind of emphasize a few things, like how many times it turns, how many times it crosses the x-axis. You'll see they all cross related to their power. This can happen in certain cases. So emphasize each of these odd degrees start with a negative in and end with a positive. Now this could be flipped, okay, depending on your leading coefficient. It says right here these are positive, so it has that sort of scenario. And then here is if I look at even. So this is 2, this is a 4, and this is a 6. What do you notice about 2? Rises on both sides. For this one, also rises on both sides. And this one as well, it's rising on both sides. So it looks like even does the same. Odd terms do the opposite for the sides, for the left to the right. Okay, so make a note of that. Now, you'll notice here all of these, if I look at the leading coefficient for all the leading terms, they're all positive, okay? So various things, I could technically have a quadratic that looks like this. It opens down, right? So an example of this could be negative x squared plus 2x minus 10, something like that. Okay. So it opens down because this leading coefficient is negative. This one here opens up because its leading coefficient is positive. Okay, so both of these examples have positive, and if they have a negative leading coefficient, you can kind of think of it as it's going to do that. It's not going to rise on the right. It's going to fall for odd, and then it's going to rise on the left. So if the leading coefficient and previous two slides have been negative, the results would be similar, but the graph would be reflected in the x-axis. Right here, a polynomial function of degree n has at most n linear factors, and you can think of that as it could cross the x-axis n amount of times. Okay, can't cross more than n. Okay. And also, if you break it down, it can have at least n distinct. Sometimes they would be the same. Okay. It follows that the graph can intersect right here, so it kind of ties in these linear factors and how many times it crosses, at most n times. Okay. The graphs on the previous slides for the odd and the even, we see that, for instance, the even, this one here, I don't even intersect it at all. And then this one here, I only intersect it twice, and this one I intersect it 3 times. So what I want to say is, for instance, for an even, you can intersect it 0 times, or 1, or twice. Okay. So for even, it's really weird, the setup here. And we can go through some practicing there. So for instance, how many times it crosses, right? If it's an x-intercept, that will be a 0 or a root of the function. So one thing you want to think about if you're talking about, let's say, a regular quadratic, I could have it above the x-axis, then it would cross 0 times across the x-axis, which means it has 0 x-intercepts. Or it can just barely touch the x-axis at one point. So it has 1 x-intercept. Or it can go through, and then it will have 2 x-intercept. Okay. So you see, for an x squared, it can have a multitude of different things. Okay. Now let's look at the cube before we move on. So let's say if we looked at x cubed. There is no possible way that the x cubed can have 0 intercepts, because if we think about it, if it starts on one end, like at the bottom here, if I want to draw it, I can go through it like this. It has to cross through just by it being odd. Okay. The even, you think, for this one, it goes up, like if I have x squared with some other stuff here that I'm adding on to it. You want to think if I take a negative number, if I take a positive number, I square it, it's both going to be positive. So that's why it's going upward. Okay. You can think the leading term is kind of controlling what the graph will do the further you get from 0. Okay, the further from the origin. So this is if you have 1 for x cubed, crosses through once. And what about if it wants to cross twice? You can do that. That one's a little, so you could do it like this, where it bounces and then goes through like that, because it is a cubed. Okay. This is 2-intercept. And then you could technically have 3, right? If you go 1, 2, 3, like that. This is x cubed to some x cubed shape, general shape. You could have other terms. But remember, the highest term will kind of help you think about what the shape could be. And this was when you have 3 intercepts. So just make a note that if you have an odd degree polynomial, so with odd degree, then it can have 1, 2, n x intercepts. But if you have an even degree, it can have 0 to n x intercepts. Okay. So one thing to note here, polynomials are continuous and smooth. What it means, if you sketch, you can do the point, you can draw the graph without lifting your pen from the paper. No sharp corners. So here you see if I was going to draw this, oh, I'm down here, then what happens? It looks like I jump up here. So this is not smooth. There's a break point. For this one, I should say it's not continuous. Okay. For this one, it's continuous because I can draw the whole thing, but it's not smooth. Okay. There's that sharp point here. So this is an example of it's nice and smooth and it turns nicely. So this is a good example of a polynomial. There is some regression here. We're not going to talk about that. You should not have any regression questions on your thing. If you want to practice this with the quadratic regression, that's up to you. You shouldn't have any on your project or your homework. So, and if you're curious, you can try this on Desmos if you really want to do the quadratic and see if you get this result. So now we're going to move on to rational functions. So rational function is when I take two polynomials and I divide them. Okay. Then the domain is what? The set of all real numbers such that I don't divide by 0. So let's say we had the following. We have x minus 3 and x minus 2. Those are two linear functions, so they're polynomials. Let's say I want to write them as a rational function. So then f of x would be n of x is on top, so that's x minus 3. D of x is x minus 2. And what's my domain? Would be all reals except when the denominator does not equal 0. Our denominator is x minus 2. So I can get any number except when I divide by 0, right? Are all reals for which the denominator, so these two are saying the same thing, and I could solve this here. So x equals 2. So I could say it's all reals except 2, right? Or you could do interval notation. Right? So it's like we just skip using 2. So that's why the 2's are in parentheses. Okay. Remember, infinities always have parentheses. So one of the part of the things with a rational function, like let's graph this and see what it looks like. Well, if we look at it graphed, We see that it's this right here. Has these some weird characteristics. Okay, you see that around 2, the function is going all the way down and all the way up. And around y equals 1, it's going all the way to the left and all the way to the right. So these are some physical characteristics that we can see, visual characteristics. So what's happening at 2, we call this a vertical asymptote. So that is a line in the form of x equals h. So in this case, it's x equals 2 is the vertical asymptote, okay, for this problem. That means as x gets really, really close to 2, close to 2, the y value goes to infinity. Let me write a better infinity. Or minus infinity. That means the graph goes up. We see here it's going up. And if it goes to negative infinity, the graph goes down. Okay. And then we can't have any value at 2 because that would be dividing by 0. You can think of this as you get closer and closer to 2, right? Like in this one here. 2 minus some value close to 2 minus 2 will be super, super tiny. So if you divide that by whatever number is on top, it's going to be very, very large. So that's how we get that sort of. So here is another one where you have vertical asymptotes at 2 places, negative 2 and 2. Right? So these are your vertical asymptotes here. And we see, in case you're curious, we also have one here as well. This is a horizontal asymptote. In the previous problem, we had one here. So this one here doesn't have vertical. This one has what we call a slant or oblique. It depends on, let's see if the notes mention one of those terminologies. Okay. So the horizontal asymptote of a rational function is in the form y equals k. It does approaches but does not cross as both x increases. That means the graph goes to the right. And as x decreases, that means goes to the left without bounds. So that means I'm looking at the right side of the graph and the left side of the graph, okay? So we see here, this is a picture where it's y equals 1. So we see here's y equals 1. And we see that as I go to the left, what's happening? Oh, it looks like it's leveling off. And as I go to the right, what's happening? It looks like it's approaching 1, okay? So some people think of this as, you can say, end behavior. So what happens at the end of your graph? Kind of, the end is in a sense as x gets really big. Like what is it kind of leveling off or rounding to and stabilizing at? And then we see here is one where we have x equals 0. Y equals 0, my mistake. It's hard to see it here, but there is that. And then this is another one where there isn't any. Has that weird slant or oblique asymptote. So how do I get how many vertical asymptotes I have? Well, you could graph on Desmos, remember. So a lot of these things, try to look at them on Desmos, see if you have any questions about them, okay? So if the denominator d of x of a rational function has a degree n, the rational function has no more than n vertical asymptotes. So what that is saying is, whatever the power on the denominator is, the highest power, you can have up to that many vertical asymptotes. Sometimes you might not if they like double or if you have triple of the same thing. Okay. So if the numerator and denominator of the rational have no common zeros, which means the rational function can't be simplified. So some questions might have it where you need to simplify, cross some things out. If you cross anything out, that's not a vertical asymptote, okay? So that's what it means by here. So if there's no common zeros, you set the denominator equal to 0, and everything that satisfies is a rational, not rational, is a vertical asymptote. Now, if they have common zeros, so one example would be, suppose I had this. Suppose this was my function. We see that, oh, this and this are the same. So that means their 0 would be 3. So I could cross those out. So because they share a common real 0, they share linear factors. So they both share x minus 3. So that means the rational function is reduced. So this thing I started with now turns into this. With one stipulation, with a hole at x equals 3. So what would that hole be? So we get that it's x equals 3, and you have to plug it back in. Okay. So let's look at this one on Desmos real quick. Okay. I think. Okay. So I'll go to Desmos here. Oh, that's too zoomed in. There we go. Ooh, too much. Okay, so let's look at y equals, let's do the fraction, divide by. All right, so let's type our top. So that's x minus 3. And then I think I had x plus 2. And on the bottom, let's put x minus 3. And then x, let's see what I had here. X plus 9, okay. So we see it looks like this, okay? So you know that graphing this, right? So one thing to note here is if you see it kind of marks where your x-intercept is at minus 2, it marks where your y-intercept is. And also, if we go over to 3, what does it say for 3? So it says it's undefined because I can't plug in 3, okay? So whatever, you always want to reduce, okay? So Desmos will not show you where any holes are at, okay? So a hole is the part that reduces out. So then you have like a hole there, like so it's not continuous at that point. So if we do y equals, let's just look at the reduced one that we said. So x plus 2 over x plus 9. We see, oh, it's the same exact graph. But what's different? You don't have that first piece that reduces out. So if I'm not even looking at the red one, if I look at the blue one now, if I go to 3, I see that I get that value. So that's where they change, okay? So what I'm saying is if you have a big rational expression that you cross things out, you need to keep track of those holes. Mathematically, those are two separate. The red one here and the blue one here are two separate functions. Okay. The first one, even though they look the exact same, first one has a hole at 3. The second one does not have a hole. Okay. And we get here that you have a vertical asymptote at -9 because you take your denominator, solve it for 0. So if you do x equals minus 9, we see we have that vertical asymptote there. Okay. But what about horizontal asymptote? Well, it looks like, and maybe it's like leveling off at 1, so let's check. And it looks like that is correct, just by looking at visually from an intuitive standpoint, where does it look like it's leveling off at? Okay. So Desmos is really good if you're trying to think, oh, is it this or is it that for those asymptotes. So for the horizontal asymptotes here, a rational function with a degree where the numerator is less than the denominator, asymptote is 0. So that means the bottom has larger degree than top. So the bottom part of the rational function, or the denominator part, has a larger degree or higher power than the numerator or the top part. So if they are equal, then you do what? You do this ratio here. Ratio is you divide the leading coefficients. Okay. So if the bottom part has same degree as top, then you divide those leading coefficients. Okay. And we'll get to one example like that. And then last part here, if the numerator is greater than the degree of the denominator, there isn't any. So bottom has a smaller degree than top. No horizontal asymptote. Okay, so if we look at this one here, I would really suggest practicing with Desmos, seeing what you can. So the first thing you always want to do is find the domain. Okay. So for this one, remember, for a rational function, domain is all reals except what makes x squared, what makes the denominator equal to 0. So if we solve this, x squared equals 4. Take a square root here. Remember, that would be plus or minus, because square root has two outputs. So this would be plus or minus 2. So this would be all reals except plus minus 2. So as interval notation, negative infinity to negative 2, union, negative 2 to 2, union, 2 to infinity. So it's quite a handful. Okay, so if I exclude two values, it's negative infinity to the smaller value, and then the smaller value to the next value. That's larger. And then the larger value, you can keep going. Okay. What about the intercepts? Okay. So you could graph this on Desmos and do it that way. So if you want the x-intercept, you solve the numerator for x. Okay. As in you set equal to 0, and then you solve numerator for x. For the y-intercepts, you plug in 0 for x. So let's look at this one here. If I plug in 0 for x, so the y-intercept would be f of 0. So 3 times 0 over 0 squared minus 4. So this would be 0 over minus 4. I get 0. So your y-intercept is 0, 0. And then your x, if you solve the numerator for 0, you would get the same result, actually. So it's not a very good question here. So just think for the y-intercept, plug in 0 for the x. If we just take our numerator, set it equal to 0, we solve for 0. You divide by your 3. So 0 over 3 is 0, so we get that. So that is your x-intercept, okay? Now for your vertical asymptote, take your denominator, so take your bottom function, set equal to 0, and solve 4x. Okay, so the bottom part is x squared minus 4 equals 0. How do we solve that? We kind of did that earlier. So x squared equals 4. Then we take the square root. Remember, you have plus or minus. So x would equal plus or minus 2 because you do the square root of both sides. And that will leave you with a plus and a minus. So we have two vertical asymptotes here. Now horizontal, we have to look at our rule. We see that our bottom part is larger than the top. So bottom has a larger degree, y equals 0. Okay, so the horizontal asymptote, y equals 0 because bottom degree larger than top degree. Okay. Now, you want to sketch a graph. I won't do this by hand, so let's look at this on Desmos for a second. So if I just type in y equals 3x divided by x squared minus 4. Look at this. Can you imagine sketching something like this? No, you can't, right? This is, whew. There's a lot of stuff going on here. You see that if I plot my two asymptotes, vertical asymptotes, I should say. Okay, we have them there. And if I plot my horizontal, we have it there, okay? So this was very hard to graph by hand, so use Desmos to help you pick the right graph on your homework. I will never ask you to plot anything by hand. Okay, use Desmos. So there's a match problem you could do here. Okay. So this talks about procedures for finding them. So you can just read through these as just separate cases. I kind of mentioned these before. If you don't reduce it, that would be case 1. Case 1 means you can't cancel anything else. So that's like the example I just did. Nothing cancels out. Case 2 would be somehow it's a reduction. So if you have something that's canceled out, you have to only look at the reduced form. And we kind of talked about that earlier when the x minus 3's canceled out. We only had one vertical asymptote. We didn't have two. So what I mean is, when we look back up here, you would expect, oh, I have two vertical asymptotes because I have two things in the bottom, x minus 3 and x plus 9. But because the x minus 3's cancel out, that 3 is not an asymptote anymore. It turns into a hole. Okay. It's still excluded in the domain, though. Okay, we don't want to include it. So be careful of that. So a good rule of thumb is look at the original expression for the domain, reduce it, and then use the reduced one for the asymptotes, okay? So just think for your domain, original, for the vertical asymptotes, it's the reduced, so original form, reduced form, and think holes. What is canceled? Okay, what is canceled? Okay. And then has horizontal asymptote here. So you'll see here it's the same thing. The horizontal asymptotes don't really have any rules. So let's look at this example. I want you to find the asymptotes. Okay. So this sort of thing, you'll need to factor it down. But let's just say, hypothetically, I'm not really good at factoring. So let's just key this into Desmos. Let's just see what the graph looks like at the beginning. So let me take a screenshot of this. And then right. So if we go over to Desmos now, let's key this in. So we see that we have that division. Okay, let's type that in here. We have 3x to the third, right? And then plus 3x, and then minus 6. And on the bottom, 2x squared minus 2. So, so it looks like we only have, right? So you'll see that the degree of the top is 3. That's already higher than the denominator, or the bottom piece. So there's no horizontal asymptote here, okay? And that will always stay. Whatever you reduce, it'll drop the power of the top and the bottom. So typically you can just look at the beginning. You don't even have to think about reducing it. Like, what would it be? So here, the numerator piece is higher than the denominator piece. So that's why we see the slant. We don't see a horizontal asymptote. And you only see another one. So you might think, it looks like maybe it's at -1. So let's see if it's at negative. You might, let's say we think it's at -2. That's a little too far, so we need to move it over a bit. So we see it's at -1, okay? But we have x squared on the bottom. So that probably means that there's something that was reduced. If you only see one vertical asymptote, but the power is 2, then either it's reduced or it's just the same thing twice, okay? So I'll go over this one real quick. So we said the vertical asymptote is x equal -1, and there is none. So you want to think numerator, larger degree. So because the top has a larger degree, it doesn't have a horizontal asymptote. Excuse me. Now for your vertical asymptote, why is it just 1? So the thing is, you have to somehow simplify this, and this can be very challenging, let me tell you. Factoring is not very good. Sometimes it's an intuitive sense of what you can do, or a lot of practice. Let me tell you, practice so many times. So that's why I said graph on Desmos to get these things, okay? So if you want to factor the top here, I can pull out a 3 from everything. Oh, wait, did I write the wrong one? Oh, I wrote the wrong one. I thought that was a 3. Hold on. I need to fix myself. So if I had this, then that would have been correct. Okay. But I made it boo-boo. It's fine. So I'll show you this, and then we can correct it on Desmos real quick. So this would be if you reduced it. So that's my mistake. I do apologize. If you now factor the top, so hopefully you recall your factoring stuff. That would be the factor form. And then the factor form for the denominator. So if you struggle with factoring, you can stop by my office hours. We can talk about it. You can set up a meeting. You can look at some of the previous things about factoring that we did in the course. Okay. So what's going to cross out? These x minus 1s. So we get the same thing here. So you'll see that even though I typed in a 3, I got the same one. It just so happens. Okay, but the horizontal asymptote will be something else. So let me go back to Desmos and re-enter this as the right thing, not a 3, but a 2. So we see we have that, and now we have a different horizontal asymptote. So the horizontal asymptote now is at, you'll think that they have the same power, so it's their leading coefficients, you divide them. So that's why it's 3 over 2, because 3 is on the top leading coefficient, 2 is the leading coefficient on the bottom. Okay. So we're going to erase this. So it would be y equals 3 over 2 And that's because the degrees are the same. It's the ratio of leading coefficients. Okay. So this is the reduced form here, and you'll see that there would be a hole at x equal to 1. So whatever value, so if we just go back over there and check real quick, we see what? If I put my finger, let me get rid of the asymptotes here. If I put it over 1, you see all right there was undefined. Hard to kind of pinpoint. You can probably do this a little bit. You see that it's undefined, so it doesn't really show us, but we know it's there, okay? So moving on, do this match problem, talk about this last part here in a moment. Hey, so we're going to talk about example 4 here. So this is employee training. So a company that manufactures computers has established that on average a new employee can assemble with the function so many components per day after T days of on-the-job training as given by this equation here. So you see this is a rational function. So you want to sketch the graph, identify any vertical, horizontal asymptotes. What does this approach? So what this is asking you for, remember T increases, T is your X. So if it increases, this means it's going to the right. So as you go to the right, what is n of t getting close to? So this is also saying what is pretty much the horizontal asymptote. So if you want to know when your function, what is it approaching as your x, or in this case your t, increases without bound, this is pretty much asking you for horizontal asymptote. So you'll see here these have the same, so the numerator and denominator are same degree. Therefore, you divide the leading coefficients. So in this case, it will be 50 over 1, because this is a 50, and there's a 1 to be understood in front of that t. So the answer would be 50. Now let's look at the graph for a second. So I'm going to go over to Desmos. So I have y equals, and I'm just going to use x instead of t. So 50t divided by, and I see if we zoom out a bit, we see that, oh, it looks like it's leveling off at 50, okay? And we see that by 50 over 1. So I hope you enjoyed this video. Let me know if you have any questions. Thanks for your time.